periodic table has just an abundance amount of information if you know how to read it and infer the information that it is there for you. And so first of all, let's talk about the folks on this side, so that go this direction. These rows are called periods, and everything coming this way are called groups. The groups have some important information located at the top of each column. And I'll focus your attention right here, like on the 7 and the 6 and the 5 and the 4 and the 3 and the 2 and the 1. This number actually refers to the number of electrons in the valence shell of each atom. And right now we haven't really defined what valence shell is, other than I explained to you that these guys here have a full valence shell. They're very inactive as far as chemical activity goes, or kinds of fun reactions we can do, because they're stable. So right now all I'm going to do is define for you is a valence shell is where bonding occurs. So that doesn't mean that there's only 7 electrons in a fluorine atom. It just means that the electrons available to bond with other atoms, that's 7. Same for chlorine. So as I'm coming down, you see these numbers here, this 9, this 17, this 35, this 53. Well, those handy numbers are how many protons each of these elements have. For a neutral atom, it's going to have the same number of protons as it does electrons. So chlorine has 17 protons. When it is neutral, it would have 34 electrons, not 7. So of those 34, 7 are the number of electrons that are doing the bonding with other elements. We're going to get to something very special about nitrogen, oxygen, fluorine, chlorine, bromine, and iodine in a second. But let's just kind of go back to what the rest of these parts and pieces is. So I'm pointing at things, I'm saying F is fluorine and Cl is chlorine. These guys are called symbols. They're the atomic symbols of the elements. The more common ones, you've heard of H2O, so it's hydrogen, 2 hydrogen and 1 oxygen. Nitrogen, nitrogen gas, or carbon, things diamonds are made of, or the lead in this pencil. Bromine, iodine, and we get down to these guys. These are kind of little radioactive fellas. So again, this column here is referred to as the noble elements. They have their valence shells completely full. They're very stable, and they just don't do a whole lot of fun stuff. But everything aspires to be like these guys. Everything here is trying to go to the most stable configuration it can possibly get to. And that's where the chemistry comes from. We come over here then, so we say, so 7 electrons in its, 6 in there, 5 in here, 4 in carbon. Come on over to this side. We have only 2 electrons in beryllium's valence shell, and 1 electron in everybody in this corner. Hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. Those guys are our alkali metals. They're very, very reactive because having only 1 electron in their shell, these guys get more stable by getting rid of an electron. So these guys are actually what we call, they'll become our ions, and they're cations. Let me define what that is. These are metals. The reactivity, well, go back for 2 seconds. These aren't abundant. These need to be harvested. So we can't just go and find a sodium ore. But these guys are abundant and easily found. Calcium, that's a big one. But also a metal ion. And these guys are also form metal ions, but a little more complicated. So we'll focus on these 2 columns right now and our halogens. So you'll see at the bottom of this guy, I have a color coding, and it defines these as halogens. Halogens are the opposite of this. These metals. These metals want to get rid of that 1 electron Well, these guys only need one to become incredibly stable. So they really want to form ions too by taking on an electron, which would make them more negative, and that would make them negative. So why am I saying that? Because the one thing that we talked about with protons is they have this thing called a positive charge. And that is just the name that we've given it. You can call it apple, you can call it orange, you can call it whatever you want. How we define it is a positive charge. Now the magnitude of this charge has indeed been measured, but how we define it, that's just the name we've given it. Electrons have equal in magnitude, opposite in sign. So we call those, write exactly what I'm saying, we call those negative charged. So a neutral atom has the same amount of protons and electrons. If I take on something or another negative charge onto this atom, onto this fluorine atom, now I have more electrons than I do protons. And that's what makes these guys negative ions or anions. So metals become cations, they're positive, and the halogens will become anions. Cool. So let's just review real quick. We have 1 electron, 2 electron, 3, 4, 5, 6, 7 in the valence shell. So all these guys, that's the number up top, is the number of electrons in the valence shell. Everyone wants to get to this magic number 8. So if they're all racing for number 8, they're either going to be willing to give up one or take more on to get to that magic number. Cool. Ions are when we have more electrons or less electrons. So if I give up an electron over here, I become positive. I never, ever, ever, never, 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 ever, ever, underline, exclamation point, give up protons. So the positive charge doesn't come from accepting or giving up more protons. Those would be nuclear reactions where we're doing fusion or fission. These guys stay put. Electrons come and go. They're fickle little creatures. They don't necessarily stay put when they're in the outer ring. So the last thing to talk about with this periodic table is you'll see this number down here as it talks about its atomic mass. So you know the upper left corner says how many protons, and then we have a number here that looks to be, if you look at it, consistently double what that number is. Well, that's because our nucleus also has neutrons. Neutrons really, really close in mass to what a proton is, but it doesn't have a charge. So neutrons have no impact on being either positive or negative. They have an impact on the mass itself of the atom. So one of the cool things to notice about this then is if I look at chlorine, it is darn near spot on 12.011. Well, there's these things called isotopes of our atoms. Now isotopes are just this atom with more or less neutrons. So if the mass is really, really close to 12 and neutrons and protons have almost identical masses, and we call it 1 AMU. It's just an easier way to write than 10 to the negative 27 kilograms. If they have the same mass, so this would have a mass of 1 and a neutron has a mass of 1-ish, there's after the decimal that changes, then I would expect this to be 12. 6 protons, 6 neutrons gives me a mass of 12. The electron mass is so small that you don't notice it. So the abundant isotope, I would say, of this guy is probably pretty close to 6 neutrons. Let's go down here. Let's find somebody that's not. 32, 34, 79. There we go. Bromine. So it has 35 protons. If it had the same amount of protons as it does neutrons, then it would be 35 plus 35 because it's really close to 1. So I'd expect it to be close to 70. This bad boy is darn near 80, that tells me that this naturally exists with a more abundance of isotopes with more neutrons than an equal count. So it probably exists on average with something, I don't know, maybe 5 or 6 more neutrons than its proton count. And so that's really cool, because you can look at these elements and their symbols, and without knowing too much about them, you can start to deduce some of the facts that are going on in their nuclei. You can look at numbers up top here and know how many electrons it has to bond with other elements. You can also look at this and you say, okay, so if this is negative, if this becomes negative because it takes on an extra electron to fill that valence shell, then it turns out that if I look at this and think about the valence shell and added electrons, I can also look at this and know what the charge would be on it. So this one would be -1 because it would take on 1 more, so 1 plus 7 is 8, -1. 6 plus 2 is 8, so -2. 5 plus 3, -3. And if this was an ion, it would be -4. That's because it takes on 4 more electrons than it would have protons. Same with this. 3 more than it would, 2 more than it would, and 1 more than it would. Come on over here, and I can do the same thing. If it's going to give up 1, it's going to end up +1 charge. Come to beryllium, it has 2. If it gives up 2 electrons, it now has 2 more protons than it does electrons. It's a +2 charge. Pretty cool. So over here, it's the difference between the 7 and the 8 is the additional amount of electrons that it would take. Those additional electrons above and beyond give it that charge. So there you have it. You have a nice overview of all the information that's available in the periodic table.